In this lesson, I'm going to show you an extremely important problem-solving tool that you could use for many different types of equilibrium problems. For this lesson, we are going to be able to identify concentrations or partial pressures of chemical species at equilibrium based on initial conditions and the equilibrium constant. So having a grasp on how to write an equilibrium expression is extremely important. Also understanding how to calculate an equilibrium constant as well. The AP curriculum point with this concept is the concentrations or partial pressures of species at equilibrium can be predicted given the balanced reaction, initial concentrations, and an appropriate K value. Now, this is beautiful and magical and deserves so much attention and glitter and pony rides and all kinds of stuff. This ICE procedure is an excellent way of problem solving for equilibrium problems. In this unit, the next two equilibrium units that we complete, you're going to be seeing this process over and over again. We'll spend a few days on problem solving using this ICE technique. The letters I, C, and E. I stands for initial, C stands for the change occurring during the process, and E stands for equilibrium. And if you look back at the free response sections of many AP exams, you'll see the first question has something to do with equilibrium most of the time, and it involves solving using an ICE problem. So let me show you how this works with a couple examples. And again, we're going to go over this in class and solve these problems in class together, but I want you to understand the format and how to set these things up before we get going. So the setup for this particular problem, we're given the initial concentration of substance A, 0.85. Calculate the final concentrations of A and B. So here's our process. Sometimes these are called Rice tables because R stands for reaction. So you have your reaction, then you have initial amounts, the change, which is based on stoichiometry, and then the equilibrium amounts. They also give us the K value. So what you want to do here is write your equilibrium expression first. So K equals, well, we know it's equal to 24, so it's equal to the concentration of B divided by the concentration of A. So now we're going to set up our ICE table. We fill in the initial concentrations that we're given. So we're given the initial concentration of A is 0.850 molar. The initial concentration of B is nothing, right? We're not given that amount. It just says we started with A. That's it. So A is going to turn into B and eventually establish equilibrium. So what we're going to do here, and you can see from this value of K, this is kind of large, right? It's bigger than 1. So when we get to equilibrium, what are we going to have more of? Are we going to have more reactants or more products once equilibrium is established? Based on this value of greater than 1 and the fact that the K value is calculated by B over A, it would be such that there would be more B present than A at equilibrium. So now we're given the initial. Now we have to figure out the change. The change of A is we know we're going to lose A because it's going to turn into B. How much? We're going to lose X amount. We don't know yet. And we know that for every amount of A that we lose, we're going to gain the same quantity of B. How do we know that? Because they both have the same coefficient in the balanced equation. If there was a number other than a 1 here in the balanced equation, that would show up as a coefficient to the X. So if A had a coefficient of 2, it would lose A at a rate of 2x. But it doesn't, so let me just take that out. So the amount that you add or subtract is based on the stoichiometry of the reaction. So now once it reaches equilibrium, how much do we have? Well, we have 0.850 minus X at equilibrium. How much B do we have at equilibrium? X. 0 plus X is X. Now we can plug in this equilibrium line into the equilibrium expression. So this is algebra. 24 equals the concentration of B divided by the concentration of A at equilibrium. So now we have to do some algebra cross multiplication here. So we'll cross multiply. So X is equal to 24 times the quantity of 0.850 minus x. We'll distribute the 24. So 24 times 0.850 is 20.4. And then we distribute the 24 over here, so that's minus 24x. And that is equal to x. So then we will add 24x to both sides. Please be careful with your math here. I mean, this is, like 8th grade math, but you don't want to mess this stuff up. Okay, then we divide by 25 on both sides. X is equal to 0.816. So now we can substitute this back into our table. X is 0.816, so now we know the value of B's concentration at equilibrium because we know that X is equal to the concentration of B at equilibrium. So there's that one. Now what's the concentration of A at equilibrium? Well, the concentration of A at equilibrium is 0.850 minus 0.816, which is 0.034 molar. So we have our two answers. Now back at the beginning I asked, at equilibrium, are we going to have more reactants or products? We said more products because it's a larger value than 1, meaning our numerator was large. Look, we have more products than we have reactants, so it holds true. Here's another problem using an ice table. We have this reaction. We're given certain concentrations of each of these ions. They get mixed together, and at equilibrium, they give us the concentration of the product. What is the value for the equilibrium constant for this reaction? So we're given the initial amounts of the two reactants. I should put the arrows in here. And we're given the equilibrium concentration of the product. How much did we start with? We started with none. So how did we get from 0 to 4? Well, we added x. What do we do to each of our reactant amounts? Well, we're going to subtract x. Why are we subtracting x? Because their coefficients are also 1s, and we have to lose reactant in order to gain product. So we know what x is equal to now because we started with no FeSCN. We added x amount and we ended with 4. So we know that x is equal to 4. If we know that x is equal to 4, we could plug that into the equilibrium line for each of the two reactants. So we know the equilibrium concentration of the iron ion is 2, and we know the equilibrium concentration of the thiocyanide ion is 6. So we have all of our equilibrium concentrations. The question is asking, what is the value for the equilibrium constant for the reaction? So the equilibrium constant is going to be based on our equilibrium expression. And all of these would be raised to the first power because all of them have coefficients of 1. We plug in our values, product 4 over reactants. And there we go. That's our value for the equilibrium constant. So that's another type of problem you could be asked to solve. For this problem, which is a follow-up to the prior one, we're going to use, this is the same reaction, so we know that our equilibrium constant is equal to 0.33 from the prior step. So we're given the initial concentrations of our two reactants, and they're asking us for the equilibrium concentration of the product. So we start with 0. Okay, we have our equilibrium expression. We substitute in. Now here's where we get a little bit tricky, and I'll show you in class several examples of problems like this. If we, I don't even know the math term for this. This is going to be a binomial, something like that. If we FOIL this, remember that term, first, outer, inner, last, you're going to get a problem. Let me find my notes. So you're going to get 0.33 equals x over 80 minus 18x plus x squared. Okay? You can get to the point where you cross multiply this. So 0.33 times this whole quantity, that would be 26.4 minus 6.94x plus 0.33 x squared. I'm sorry, this is 0.594 or 5.94 equals x. And then we can subtract x from both sides. And then what you could do here is you could use the quadratic equation to solve for x. And once you solve for x, you have the equilibrium concentration. You have a solver function on any graphing calculator that will allow you to solve the quadratic equation. AP questions really haven't given you problems like this where you'd have to use a solver function. I will show you situations where you might get to this point, but there are certain conditions and certain values for equilibrium constants where it's not going to be necessary to deal with the minus x portions, and I'll explain that in more detail. I just want you to have an idea of how you would set a problem like this up. I'll show you an example using the solver function, but you're not going to have to do that on an AP question. Here's another one of these problems, a mixture of 0.5 moles. This is the last one. A mixture of 0.5 moles of each are placed in a 1 liter flask. It gives us the K value. Calculate the concentrations at equilibrium. So they're both placed in a 1 liter flask, so 0.5 moles over 1 liter is 0.5 molar. So we have our initial line filled in. So now we know we're losing hydrogen at a rate of minus x, iodine at a rate of minus x, and we're gaining hydrogen iodide at a rate of plus 2x because of its coefficient. Okay, we're given the K value. And our equilibrium expression will be HI quantity squared H2 I2. So 2x quantity squared over 0.5 minus, 0.5 minus x quantity squared, and that's equal to 54.3. So again, you're going to get to the situation here where you're going to probably have to work through a quadratic. And again, I'm not going to harp on that because it doesn't come up. I'll show you again how to do it. But it's just a matter of, if you use the solver function, it just asks you to plug in a, b, and c, like ax squared plus b x plus c equals 0. You plug in your a, b, c values and it gives you your value for x. But I'll show you examples that are more likely to occur where the x would be negligible. That's this point here, and you'll see we'll do several examples in class. If you have small k values, small equilibrium constant values, the x might be negligible. If your x is not negligible, it's a type of problem where a quadratic's not going to be necessary. You'd be able to get x directly and solve from there. This is also very important. If you have the examples that we were looking at, we were given initial values for like the reactants, and the initial value for the product was 0. So we knew that this would have to be gained and this would have to be lost. If you're given a problem where you are provided with initial amounts of all of your components, so like your product doesn't start at 0, what you'd first have to do is calculate Q, compare it to K that you'd be given, and then determine who's gaining and who's losing here. Because remember, if Q is less than K, the reaction will go forward. A and B would be lost, AB would be gained. However, if you calculate Q and Q is greater than K that you'd be given, the reaction would proceed in the reverse direction, in which case you'd lose AB and you would gain A and B. So we'll look at a couple examples of those in class as well, where you're given starting amounts of all of your reactants and products. There's no zeros anywhere. You have to calculate Q first and then determine which way the reaction will proceed. Will it proceed in the forward direction or in the reverse direction to establish equilibrium? So I hope you have a basic understanding of how to set up an ICE table, what the letters mean, and how we can go about performing various problem-solving techniques using an ICE table. Something else you'll have to be able to do, obviously, is figure out if something's at equilibrium or not using a Q value, and use the ICE tables to calculate things that are not at equilibrium.